if I have P equals 7, Q equal 11, I think this example we've seen before. I compute N is PQ, which is 77, and P of N is P minus 1 times Q minus 1. That's a formula, but P of N should be the number of coprime remainders modulo 77. So I know we haven't shown that. We can either count the coprimes modulo 77, or we could apply this formula. So that would be, of course, 6 times 12, 6 times 10, right? That is 60. Let's have my steps here. And then I choose small prime E as public key. So let's choose E here, 13. Then I need the RSA equation that says ED has to be phi of n times something plus 1. Sometimes this is called condition. This RSA wouldn't work if E and D don't satisfy this property here. Now that's the same as saying, same as D has to be E minus 1 modulo P of n. It's the same thing, because this one's saying E times D have to be 1 modulo Phi of n. That means 1 is the inverse of each other. Please make a note that this is mod Phi of n. That is, D has to be 13 minus 1 modulo 60, while the operations of RSA will be modulo 77. So there's two modulos going on here. Now I have to compute the inverse of 13 modulo 60. So one way to do that is with extended Euclid, for example, right? So I want, how much is 13 minus 1 modulo 60? I do extended Euclid, 60, B is 13, Q is 4, R is 8, right? Yeah, right? 4 times 13, 52 plus 8, 60. So then I move into A equal 13, R equal 8, Q equal 1, R equal 5. So from AB I move to BR. This is the regular Euclid. Then A equal, that's B. A equal 8, B equal 5, Q equal 1, R equal 3. A equal 5, B equal 3, Q equal 1, R equal 2, A equal 3, R equal, B equal 2, Q equal 1, R equal 1, A equal 2, B equal 1, Q equal 2, R equal 0. That's where I stop, right? Because R is 0. So who's the GCD? This is the GCD. Last B. I'm not surprised to see 1 as a GCD, because if GCD wouldn't be 1, I would not have an inverse of 13 modulo 60. So now that I'm here, I'm computing the coefficients x and y, right? So I know the last line. This goes backwards, goes up now. So this is 0 and 1. That's always true. The verification is 2 times 0, A times x plus b times y. That's 1. That's good because it has to be the GCD. Then how do I move from here to the next line? This y becomes 1 here. And in here I have previous x 0 minus the quotient 1 times the previous y 1. That is minus 1. Let's do a verification here. 3, that's a, times 1 plus b 2 times coefficient y minus 1. That is 1. Right? Now moving to the next line, this is minus 1. I'm just copying the y. The previous y minus 1 moves in here. In here I have the previous x, that is 1 minus the quotient 1 times the previous y, that is minus 1. 1 minus 1 times minus 1 is 2. So what do I get? 5 times minus 1 plus 3 times 2. That's 1. Good. This is very fast. Okay, keep going. This I have here a 2. I just copy the y here. And then here I have the previous x, that is minus 1, minus the quotient 1 times 2. So that is minus 3. Verification, 8, that's 8 times x, that's a 2, plus b, it's 5, times this is minus 3, it's 16 minus 15, that's a 1. Good. Keep going, minus 3 moves in here. In here I have the previous x, 2, minus the quotient, 1 times this guy, minus 3, previous y. So now I have here 2 minus 1 times minus 3, that is 3 plus 2, that's a 5. So verification, a equals 13 times minus 3 plus b is 8 times 5. 13 minus 3 is minus 39. 8 times 5 is 40, so that gives me a 1. Last line, 5 moves in here. This is the previous x minus 3 minus the quotient, that's 4, times this value, 5, previous y. So now minus 3 minus 20, that is minus 23. So verification, last one, 60 times 5 plus b, it's 13 times minus 23. How much is 13 times minus 23? Anybody? 13 times minus 23.
Negative 299.
Negative 299 plus 60 times 5 is 300. So how much is it? 1. We got it. So the final step of extended Euclid is to write down the box. Ax plus by is the GCD. A for me was 60. X for me, the last x is 5. B was 13. The last y was minus 23. And the GCD was 1. So the coefficient I found was 5 and minus 23. Right? Those are the x and y. And now we know that from those coefficients we get the inverse. We wanted the inverse of 13 at minus 1 modulo 60. That would be the coefficient of 13. That is minus 23 modulo 60. So that would be 37. So now that I have that was my TD, right? Now that I have that, I can do RSA operations. So how do I perform RSA? I have a message. Let's say the message is x equal 15 I can encode it or encrypt it. That is, y would be, how do I encode things in RSA? I take the message, raise at power e, modulo what? No. 77. It's modulo n. So n for me was 77. So this is 15 at power e. E was 13. Modulo 77. It turns out this is 64. So that would be my encryption. Let's write it here, equals 64. Now decryption, how do I get back x? I raise y at power d, modulo 77, that is 64 at power, what did I compute d to be? 37, modulo 77. So I have to compute this, and I think I'm gonna get, maybe the easy way to do it is 64 at power 10, everything at 3, times 64 at 7. And I think if you do these calculations, I think I'm gonna get back 15. That's something for you to verify. Do I get back the 15? I think I do. My calculations in papers like I do. I should get back 15. Right? Take another message. If I encrypt 20, the y would be 20 at power 13 mod 77. If I do the calculations, I get 69. Backwards, if I want to get back the value, that would be the original message 64 at power 37 modulo 77. If I do the calculations, that would be back to 20. So that is RSA. Now, there is a setup part, which is in here. P, Q, N, P of N, choose E, compute D. Absent other methods, extended Euclid is the fastest thing on average. Now you could do guessing or powers if you like. I computed D here 13. That's where the setup ends. E and N are public, so to encrypt things I need E and N, which are public. To decrypt things I need D and N. D is private. N is public. Let's do another setup here. Suppose I want to set up a different RSA. I'm going to use different P and Q now. P is 7, Q is 13. So N will be 7 times 13, 91. P of N would be 6 times 12, 72. Choose E, small prime. So maybe I choose E equal 11. And then from here, D it's going to be 11 minus 1 modulo what?
72.
72. That's the same as saying E times D have to be phi of N times something plus 1. Same thing. Because phi of N is 72. Now, of course, I need to compute the inverse of 11 modulo 72. So I could do extended Euclid. So extended Euclid with A equal 72 and B equal 11. A 72, B is 11, the quotient is 6, remainder is 6, right? 6 times 11, 66, plus 6 gives me 72. I go down, A equal 11, B equals 6, quotient is 1, remainder is 5, A equals 6, B equals 5, quotient is 1, remainder is 1, A equals 5, B equals 1, Q equals 5, R equals 0. That's stopping. Who's the GCD? The last B. It's 1, that's good because I want the inverse. If it wouldn't be 1, I wouldn't have an inverse. Now I need to go back and compute X and Y and verify that my coefficients work. As always, the first coefficients are 0, 1. Those are not unique values, but 0, 1 always work. You could pick 1 and 1 minus q, for example, but easiest ones are 0, 1. A times 5 times 0 plus 1 times 1 is 1. That's good. Now I move the 1 here. This is going to be 0 minus the quotient is 1 times 1. That's minus 1. So then I get here 6 times 1 plus 5 times minus 1. That's 1. Good. Now I move this minus 1 here. Here I get previous x minus quotient 1 times this is minus 1. 1 minus 1 times minus 1. That is a 2, right? So then I get 11 times 1 plus 6 times 11 times minus 1. 6 times 2, that is minus 11 plus 12, that's a 1. Then finally, I move this 2 in here. In here I have previous x minus the quotient, that's a 6 times this value, 2. That is a minus 13. So verification, 72 times 2 plus b, that was 11 minus 13. How much is 11 times 13? Hmm?
143.
And 72 times 2?
144.
So this would be 1. Now I put the box, ax plus by is the GCD. My a was 72, the x I found is a 2, b was 11, the y I found is minus 13, and the GCD was 1. That is my extended Euclid answer. X is here, y is here. Now, I want the inverse of who? I want the inverse of b. I was looking at the inverse of b mod a. So inverse of b mod a, that is the inverse of 11 modulo 72. That is the coefficient y. So that's going to be minus 13 modulo 72. Well, how much is minus 13 modulo 72? Hmm?
Yeah, 59.
59? So finally I got my keys. That was my D. E was here, D was there. So now if I wanna use RSA, that's the setup. How do I use it? If I have a message, for example, x equal 10, when I encrypt, I get y equal 10 at what power? How do I encrypt?
Yeah,
Where is
11.
E? 11. Modulo what?
91.
Modulo n. So that's modulo 91. Now, if I compute these values, you should check this at home. I have here minus 9, which is the same as 82, modulo 91. And if I want to decrypt things, to get back x, I need to take that value y, that is 82, at the power d, right? To decrypt, I raise a power d modulo 91. So my calculation is that this can be computed, for example, as 82 at power 3 at power 17 times 82 at power 2. The reason is 3 times 17 is 57, plus another 2, that'd be 59. This in here gives minus 1. So the whole thing will be minus 1 times 82 squared turns out to be 81. So that is minus 81, which is of course the same as 10, modulo 91. So I have the RSA, which is a setup, includes P, Q, N, P of N, E, and D. That's a setup. To encrypt things, I need the public keys N and E, and to decrypt, I need N, which is public, and D, which is private. D is secret. Only people with D can decrypt things.
3 times 17 is 51. 57.
3 times 19 then?
Yeah.
Minus 1 at 19 is still minus 1. So it works out. Sorry. Yeah, very good. I'm glad somebody's following calculations.
We trust you.
Yeah, that's no good. Math, you have to check, verify, check, you know. Okay, so that's RSA in a nutshell. Now, we said something last time about signatures. So we kind of were in a rush and we didn't quite say it well, but we're going to say it now again. I'm going to erase this part here. This is an example of encryption decryption, but the principle is, so I have message, encrypt, decrypt. If the message is X, the encryption is going to be Y equal X at E mod N, and the decryption is going to be X equal Y at D mod N. Right? That is the idea. And here's an example of how that works. Now, what I would like to do, the signature, so this is the basic RSA. Call it RSA basic. But what if I want to do RSA signature? In signatures, I want not just only to decrypt the message, I would like to also verify that the sender is who the sender claims it is. In here, anybody can encrypt a fake message. E is public, right? So anybody can encrypt E, send it to me. I'll decrypt it. Now, only I can decrypt it because I have the D. Nobody else can. But when I decrypt it, I get back X. And now, I'm not verifying who sends this message. If the message was fake, is one encrypted fake, I'll get a fake message. So there is a adversarial intrusion effect here, which is I would like to verify that whoever sent me that message or that email or that certificate or that whatever I'm getting is actually sent by the person saying it is, not by somebody else. So how do I do that? Right? Again, we said this last time a little bit, but it's not quite right. If I have it here somewhere. Yeah. So here's what I can do instead. I have X, my message, and what I can do is the encoder first will have to encode X, but with with its public key. So it's X at E. Now, that's weird. I'm encrypting stuff, sorry, with D, with the private key. So I'm encrypting with the private key. And then I put the signature here. So I'm gonna say, in here I have, here's Alice, the encryption. And here's Bob, which does the decryption. So Alice is going to use a private key first to encode the message. Then he's going to write down Alice. And then he's going to put the message, the plain message. It's going to take the whole thing and encrypt this normal, like with the key E. So take the whole thing, raise it at power E. So what's the difference between this and this? In here, the message is X, just like in here, and the basic encryption is raise X to the power E, like in here, X to the power E. But apart from this message, Alice is also sending the signature. This is the message. Observe that the message is the same as before. No difference. I'm sending the message, but not just the message. I'm also sending a signature. For signatures, I'm encrypting with the private key. Now, you could ask, okay, let's check the math first, but then how does Alice know the private key? Right? If private key is supposed to be secret, well, how come Alice has it? Right? We'll get there. Just to figure out how the mechanism, what is Bob going to do now?
They're the same private key, right?
That's the key. They're not the same private key. But we'll get there in a second. What does Bob do to get back this stuff? Well, Bob does the decryption first. So Bob will take this Y thing, right? Bob will take Y and say, well, what happens if I raise Y at a private key? Modulo N. What will happen? Any message at power E. Now the message, you have to think of the whole bracket as the message, right? So the message is not just the original message, it's a message plus some other stuff. Like with any message, if I raise it at power D, I get back the message, right? So the message would be what? What am I getting back? I'm getting back X at D, I'm getting back Alice, and I'm getting back the original message. Right? So it's kind of applying a function that worked before for any message. Now we are applying the same procedure or function, but not just to X. We're applying to the X and signature as the package. So when we decrypt that package, we get back the whole thing. That is the original message, Alice the name, and so we're getting back a signature and the message. So now Bob has one more step to do. Bob will read the word Alice separately and say, Alice. That's the sender. Just in case I don't trust my email client, because emails, for example, say this comes from Alice, right? Maybe I don't trust that. It's safer to read it from inside the encryption. And so I read that from here. And then what Bob is going to do as a second step is going to say, I'm going to take this X to the D and I'm going to raise it at power E. That's the public key, E. And I'm supposed to get back something, let's call that X prime. Right? When I get X, I raise this part, the signature, at power E, I'm getting back X prime, and then I'm checking if X prime is equal with X. Yes?
Is this all modular?
Yeah, that's all modular. Like before, everything is modular. So Bob does two steps now. Gets the message, decrypts it like before. It's raised to the power D gets back. Now Bob breaks the message. He knows the message is going to be broken into the original message, Alice the name, and the signature. Takes the signature, raised to the power E, see what that is. And then he checks, is this the same as X, which is here? If yes, what does that mean? Alice is valid. The person who claimed I was Alice must have worked out. Why is that? Only Alice could have encrypted with this D so that when you decrypt to D, you get back the original message. If it's no, then say Alice is not valid. So if I don't get the same message when I get the message at the first step and the decryption at the second step of the signature, if I get different things, I'm saying something was off. Somebody interfered here with the wrong key. How many people follow me? Now, there is, mathematically, that's what we want. But there's this question, okay, well, how does Alice knows D, the private key? So what people are going to do, each person is going to have a public key and a private key. If you ever set up an SSH key authentication, you set up a key, right? Now, your key is different than my key. We don't have the same SSH key. So everybody has their own keys. So what happens here, Alice has a private key and a public key and a modulo of her own. Her modulo can be 77 and Bob's modulo can be 90, what did we do, 91, right? They don't have to have the same n. And Bob has its own private key, public key, and its own modulo. Now, like before, public keys are public for everybody, and ends are public for everybody. So what's the only thing that Alice has private? DA, it's private to Alice, right? So this is the only thing that's private to Alice. Alice, of course, knows everything else. AA, NA, and EB, and B. Everybody knows this stuff. And what is private to Bob? The DB is private to Bob. D, it's only one person who has D. Virgil has D for Virgil. Alice has D for Alice. And Bob has D for Bob. Right? The private key, never give it away. Now, how would this stuff work? What Alice can do, when it uses the D, it uses what D? Huh?
Your private key.
Because there would be no way to use Bob's private D anyway, because you only have your private. So this in here is DA. Right? Okay. So if this is DA, but of course Bob doesn't know. Bob doesn't see X at DA here. Bob just sees something. And it takes that something. That would work for Bob, right? It doesn't have to have DA. What Bob takes this part, raise it at power. What E is necessary here to make it work? DA would work with what E to give you back the message?
Yeah.
EA, right? So it have to work with EA. Is it necessary for Bob to know DA? No. Bob could just take whatever it's here, raise that power EA. How does Bob know to use EA and not E Virgil?
Because Alice is given.
Because it's written right here, Alice. So the moment Bob sees Alice in here, says, aha, Alice claims to have sent this message. So to verify it, I'd use what key? Public key of Alice, not of Virgil. Right? So the reason I know this A is because I read Alice, and then I know I should use the public key of EA. Does Bob have the public key of Alice? Yeah, public keys, everybody has them. Okay. How about this part? What D is this? When Bob decrypts the first message, the whole thing. What D can Bob have? DB, right? So that has to be modulo NB, and this has to be modulo NA. Right? This operation DA and AA would only work modulo NA. Is NA public?
Yes.
Yes, so Bob has it, right? But it's not the same as NB necessarily. How can now Bob has to use DB here, so what E has this one? What E is necessary here? EB, so that Bob can use DB on top of it. So this whole operation has to be modulo. And what then?
B.
And B. But this right here, this X at DA has to be modulo this part. Is modulo what?
Yeah.
NA. So now, what, again, if we read it again, what Bob does, it uses his private key DB. How does Alice knew how to use, Alice in here uses her key, that's easy, right, the private key. But how does she know to use EB here? Why she uses EB and not E Virgil?
Because she's sending a message to Bob.
Because she wants to send a message to Bob. So the moment says, I want to send the message to Bob. This part is the same. This part, if Alice wants to send a message to 5 people, this first part is the same for all 5, right? It takes the message, encrypts with her own key, puts there the signature Alice, and the message in plain text. Then if he wants to send it to Bob, the message to Bob encrypts with Bob's public key, which everybody has. Does Alice have EB? Yeah. And then if I want to send it to Virgil, I take the whole triplet and again encrypt it with Virgil's public key, E Virgil. So I'm sending to Bob something. Bob, whatever he gets, Bob gets a thing that he doesn't know what it is. Bob gets Y. I should call this Y Bob, because if I send it to Virgil, it's been a different Y. Right? If I send to Virgil, I will send the same triplet, but encoded with the Virgil's public key. Bob gets this. And then what Bob does, the first thing uses his private key to decrypt it. Only Bob can do that. When it decrypts, gets the triplet, and then it says, that's Alice. Let me use the public key of Alice on top of this signature here. If I get the same as the original message, I verified that the sender was Alice. How many people with me? All right. This will require some sleeping on it, I think. Yes.
In like a real world sense, how does like the sharing of all the keys work? Like how do I get your key?
I think the basic answer is in Linux, Unix-based systems, is based on permission. If you look at the .ssh folder, the private one, only you can read it. It relies on the operating system permission.
Oh, okay.
The public one, it's all readable. So everybody can read. But there are more fancy mechanisms to do that. But the basic one is use the the file system, attributes, and says that's only readable by you. Now, of course, like before I mentioned this, root administrators, in certain systems, they can see everything, even what's only readable by you, because they can change the attributes of the file. So to some degree, you gotta trust the system administrators or the people who run the setup that they're not gonna do funny things on you. Typically, administrators have access to everything anyway. So to some degree, you gotta trust the people who set this thing up to do it right. But that's not a main concern. A main concern is if you trust the administrators, how can you now know that the sender was indeed who they claim it was, that no one else could have put a different message, you're the only one who can decrypt it, stuff like that. So RSA is very good at this stuff. Why is RSA so good at it? We talked about this before, right? So the one thing that we can notice here is that the whole RSA, the principle, the mathematics, and even the operations do not require n equal p times q. The whole, if you pay attention to RSA, we always set it up with n equal p times q. But that's not necessary. The math would work for any n. This encryption, decryption would work for any n. The question is, this makes it hard to break. The reason we like p times q is not that the math is necessary for p times q. Math would work even if I put a prime or if I put a product of things. If I can choose n equal 48 and the math would work just fine. Right? I still have that fundamental condition E times D to be 1 modulo phi of n. Well, why do this? It turns out finding D, the private key, is equivalent to finding phi of n, which is equivalent to factorize n. That is, observe that P and Q are secrets. So P and Q are not given to the public. Just N is given to the public. So we know that if somebody breaks into RSA, that is find D, that's equivalent mathematically. That's a little complicated to prove. We're not going to do that. It's the same as finding phi of n. And finding phi of n is pretty much the same as factorizing it. Of course, if I factorize n, it's easy to find phi of n. And if I have phi of n, it's easy to find D. It turns out those three things are kind of equivalent problems. Solving one would solve the others. That's why we like P times Q. P times Q, it's hard to factorize. If I use n equal prime, what's the problem with that? What if I use, say, n equal prime 37? Why that's not a good choice?
P of n is just n minus 1.
Phi of n will be just n minus 1. And that will be extremely easy to find if I have n. N is public, right? So phi of n will be just n minus 1. Too easy to find.
Have they proven that it's impossible to find phi of n without knowing
Knowing the factors.
factorizing n? Or
I don't think there's a complete proof, but there's been a lot of progress in number theory on that. Most people believe, I think that's true. Or that even if it's not perfectly equivalent, it's in the same class of difficulty. Like maybe it's not perfectly equivalent, but it's equally difficult in terms of computation. If you have to spend 100 years factorizing a number, and it turns out you can compute phi of n in only 85 years, that's still good for cryptography, right? The real question is not mathematical. In practice, the question is how much computation do I need to break RSA? He's right. We don't need to factorize. All we need is phi of n. Finding phi of n will give me D with extended Euclid, which is a fast algorithm. Extended Euclid is not a computational problem. So you notice that extended Euclid is not in here. Finding phi of n will give me D. Just like I did on the board. That's how I found D, right? With extended Euclid. Extended Euclid can be implemented very fast. And so finding phi of n is the key. That's why too easy to find. How about n is the product of 3 primes? Would that be any additional benefit? Is it? Well, then phi of n, guess who phi of n is going to be in that case? Anybody can take a wild guess? Yes.
P minus 1 and Q minus 1, minus 1.
Good guess. Right? Yes.
Isn't it n times 1 minus 1 over P?
Same.
Same thing?
If you work it out a little bit, you get the same formula. That is the same as PQR, that's n, times, what did you say? 1 minus 1 over P, something like that?
Times 1 minus 1.
Isn't that the same thing? If you multiply this, you put P in here, Q in here, add in here, you get P minus 1, Q minus 1, R minus 1. Same thing. Right. Would that work for RSA? Sure, it will work. Is it be hard to factorize? Yes. It's a perfectly valid RSA, but it's no additional benefit to just P times Q. Factorization, it turns out, it's the difficult factorization is on the big numbers. If I could factorize PQR into, say, PQ times R, then the second factorization to break PQ into factors will be a lot easier. The smaller the number is, the easier it is. So there's no additional benefit in requiring 2 or 3 or 5 factorizations, because the really difficult one that will take most of the computation, factorization is an exponential type of problem. So if the number double, computation is gigantic. So the hard part, the key Achilles heel of RSA breaking is the first factorization anyway. So there's no additional benefit in breaking further into smaller factors. That once I break it once, the rest will be easier anyway. So while this is a valid system, it's not harder to break than just having P times Q. So now, we want to talk a little bit more about this phi of n, and in particular, Eulers Theorem. That was saying if A and N are co-prime, then A at phi of n is 1 modulo n. Now, this theorem is fundamental for number theory. That's what makes the RSA equation work. That equation, what was it? ED is 1 mod phi of n. I should write it here. The reason RSA works, and but the reason this equation makes it work, is specifically because of Euler's theorem. Because if ED is 1 modulo phi of n, that guarantees that when I do encryption and decryption, X at ED is going to be X at E at D, that's encryption and decryption, right? Mod n, that's going to be X. Can everybody see this? Why ED equal 1 mod phi of n implies X at encrypted and then decrypted will give me back the original message? Because ED is 1 modulo phi of n. That means X at phi of n will be 1, so X at ED will be X at 1, which is X. We said this already 3 or 4 times. But that's absolutely required and critical in RSA. Euler's theorem, which we proved in class. If I choose ED with this property, that's the same as saying ED is phi of n times something plus 1. So X at ED will be X at phi of n times something plus 1. X at phi of n is 1. Therefore, the result will be X. That's guaranteed that when you encrypt and decrypt, you get the original message back. Right? So that was the critical mathematical fact that we needed. A at phi of n is 1 modulo n. So how would this work for some particular cases? Like we said here, n equal prime. Who's phi of the prime number then? Let's say p, because I like p for prime. Remember who phi is by definition? Phi of n was the size of Cn, which is the size of coprimes, remainders. Right? That was phi of n. It was counting how many coprime remainders I have. So for a prime number, how many coprime remainders I have? Question. P minus 1. Right. Why is that?
You don't have
Because C of a prime is who? Who are the coprime remainders with a prime value?
1, 2, 3,
1, 2,
6,
up to?
P minus 1.
That's the same as saying that ZP, the whole, ZP is the whole set, minus there is only one remainder that's not coprime. Zero. So you guys know this sign? This is a set, that's another set. The minus sign between sets, hands up who knows that. Hands up, who knows the minus sign between sets? We don't know this notation, A minus B between sets? We don't know this notation, A minus B.
No.
Are you guys kidding me? Okay, what is it? What's the mystery? Who is A minus B? Those are sets. This is the number of students in CS 1800, all of them 600. And this is the number of students in the honors section. Not the number, the actual set. This is the students in CS 1800. This is the students in the honors section. Who's A minus B?
You remove all elements from A that are in B.
Right. So it's all the elements in A, but not in B. B doesn't have to be a subset. B might contain additional students from other classes. That's okay. We only care about the ones from A, but not in B. B is not necessarily a subset. We haven't seen this before? Okay, Europeans studied this in like 4th grade. You could argue that Europeans don't study literature, geography, and biology, sure. But they do this in the 4th grade. Okay. So, ZP is all the remainders. This is only a set of one remainder, 0. Everything else remains what's in Z. So who's this? This is all the elements in ZP, right? Except 0. So this is another set notation that says everybody in ZP, but not 0. Right? I mean, it's okay. This is very simple stuff. Once you see it once or twice, it will be easy. So what is Euler in this case? If I restate the Euler's theorem for this particular case, what do I get? If A is co-prime with P, that means everybody effectively except 0. That's the same thing as saying if A is not 0. Then, what the Euler theorem reads in this case? A at what power? Phi of n is who? P minus 1 is 1 modulo P. And I also have here P has to be a prime. This theorem has a name. It's called Fermat's theorem. We should say little theorem. Why we say little? Anybody knows that? Why we call this Fermat's? Why don't you say Fermat's theorem like for everybody else? We say Fermat's little theorem. Anybody knows this?
Is that how we describe it in his book? He says like, I have a little theorem to prove this.
No. Little comes from a different. Yeah. That little comes from a different reason. Yes.
Did he write it in the margin?
What?
Did he write it in the margin?
In a what?
Did he write it in the margin?
No.
She had an idea.
Did he also have a big theorem?
There is a big theorem.
Wow.
Fermat's big theorem, which is not this one. That's the most famous statement in all mathematics, Fermat's big theorem, and it has not been proven for 450 years. Only the Fermat was living in like 1600, something like that. He stated a theorem that's extremely easy to state, extremely easy. Not part of our course, but I'll make a parenthesis here. Fermat's big theory states that the equation an equal bn plus c to the n has no solution for n bigger than 3. You guys know Pythagoras theorem? A squared equal b squared plus c. There's plenty of solutions to that one. With ABC, the solutions A, B, C, and n have to be integers. So that's what Fermat's big theorem said. Not proven for 400 years. Only very recently, okay, like about 20 years, somebody proved it in England. Very famous guy. So it has been proven. The statement is very easy. The statement is easy to state. Fermat's on everybody in the 4th, 5th grades can do it. The proof is gigantically complicated. It took years and years and years for people to understand the proof. Okay? It requires very fancy mathematics. So that's the big theorem. We don't need it. It's still part of number theory, but we don't need it. We need a small theorem, the little theorem, which says it. And for us, this theorem, it's just a particular case of Eulers theorem, which is a more general case. If we have not proven Eulers theorem, suppose we don't prove Eulers theorem, like the regular sections, they don't prove Eulers theorem. How do we prove this? Is there a way to prove this without Euler? Say, okay, pretend we don't know this theorem here. Because if we do, it's just a particular case. If we don't know this, how would you prove such a thing? If I put this in the meter, can you prove it?
Without using Eulers?
Without using, because with Eulers it's easy. You just say apply Eulers for the p prime. That's it. So how about we do a second proof of Fermat's theorem? This proof is in the book, also in the notes. It's a proof that says if you are a poor mathematician and you don't know Euler, well, here's how you can prove this without Euler. But that proof is only good for Fermat. It's not good for Euler. Okay, it's just proving a particular case. Here's what the proof says. Take my A and construct this set. A times 1, A times 2, A times all the way to p minus 1. That's a set of values, right? I'm multiplying A with everybody in CP here, not 0. And it says, you know what? This, I think, is the same as 1, 2, all the way to p minus 1. It's the same set, which, of course, is CP, is the co-prime. Why is that? Why by multiplying A with everybody except 0, I get back everybody except 0? Anybody knows this?
Because if we're doing it like modulo.
Everything is modulo, of course. This is mod p. All the multiplications are mod p. Why is that?
Is it because like it's doing things use times, like you can't like you can't multiply things together.
Right, that's the intuition, but how do we say it nice? There's two things that we want to do here. First of all, if I multiply two of these things, am I guaranteed to end up in this set? Well, if I multiply two remainders, I'm going to get the remainder, that's for sure. But to be in this set, I have to make sure I'm not getting 0. Right? So the first question is, anybody in here, surely it's a remainder. But why it's not 0? Why multiplying two of those things cannot be 0? Yes. Because the only way to get 0 in ZP is to multiply with P, right? There's no way to get a multiple of P. P is a prime number. So see, with 6, maybe you multiply with 2, then with 3 you get the multiple of 6. But to get the multiple of 19, which is prime, the only way to do that is to multiply somewhere with 19. Hands up who's with me. The only way to get 0, so when I do A times any value U, so pick U in CP. A times U cannot be a multiple of P. Because P does not divide A, P does not divide U. There's no way this product out of a sudden has P as a factor. Is there a question in there? No. Okay? So that says everybody in this set is this set. That's not finishing though.
So does that mean that the order is successful?
No. The order is not the same. In the next module, we're going to distinguish a set from a sequence. When I say sequence, I'm actually counting the order. Right? 1, 2, 3 is not the same as 2, 3, 1, not the same as 2, 1, 3 as a sequence. But as a set, there's no order. So the 1, 2, 3 set is the same as 2, 3, 1 set, is the same as 1, 3, 2 set. We know that? In sets, there is no order. Those are sets. When we say sequences, that means the order matters. Okay? Now, so that's one piece. Everybody in here is in here. Now I'm going to say, yes.
Oh, when writing the set of multiples of p, do we count 0 as a multiple?
Yes. In this case, reminders, 0 is the only multiple of P. Now I'm going to say one thing in here that's new. You have not seen that idea before, okay? So that's a brand new introduction of an important idea in mathematics, which is, if all these elements are different, I'm going to say, if you pick 2v in CP, A times U is different than A times V. That means when I make this product, I'm not getting any value twice. Every one of these products are different values. This is not a new idea. We've seen it 2 lectures ago. Remember when we were thinking of that PA times QA, we said every time you pick a power of A times a quotient, you get a different product. That's the same idea. That's very easy to show. Why is this true? If U, what I'm saying here, U is different V, then AU is different from UV. It's a very easy thing to show. A has an inverse, right? So I could multiply with the inverse. If those would be the same value, U will have to be equal with V. I don't know if you guys follow me. I can say by contradiction. If those are to be the same value, A has an inverse, I multiply with the inverse, I get U equal V. So the only way to get different, if I pick 2 different UVs, I'm going to get 2 different values. But what I'm going to say here is that because these sets, so this is set on side A, let's say this is set A, and this is set B. Set A has P minus 1 elements. Because every time I make the product, I get different values. I have 1, 2, 3, P minus 1 elements in here. And if I have P minus 1 elements, and then here I have P minus 1 elements, and everybody here is in here, those sets are the same. So that would mean A equal B. Let me state this again. First part, do you guys know this sign? A included in B? We know this sign? So what did I prove here? Every time you make a product, you end up in this set. That means A, this set, is part of B, A included in B. This other part says, every time you make a product, you get different values. Therefore, I can tell you how many values you have total. 1, 2, 3, P minus 1. P minus 1 elements. Now, what I'm saying is, that's a new idea that perhaps you have not seen it. If A included in B, but the size of A is the same as the size of B, that is, I have P minus 1 elements. Obviously, this one has P minus 1 elements. The only way to do that is to be the same set. If it's a subset that has all the size as the bigger one, then it means it's the exact set. May sound trivial when somebody said it. It's actually an important piece of set theory. So A equal B, that means I prove that those sets are the same. You can see how difficult this simple theorem is without Euler, you know? So we're not done. We have to do something else. Now we have to do some calculation. So, okay, if the sets are the same, guess what we're going to do with them? Sets are the same. We're going to say, so we're continuing this proof from here. Second proof of Fermat's theorem. The first part is to prove that those sets are the same. Now, if the sets are the same, part number 2, if A equals B, the product of all the elements in A is the same as the product of all the elements in B. So if A equals B, means if I make that product A times 1, then A times 2, then all the way to A times P minus 1, this product has to be the same as 1 times 2 times P minus 1 mod P. Two sets are the same, so I'm making the product of all these elements has to be the product of those elements. How many A's I have here? P minus 1, so that's A at p minus 1 times, let's just say this is, how much is 1 times 2 times p minus 1? Factorial, right? We know that? N factorial is 1 times 2 times 3 all the way to n. So this is p minus 1 factorial. And what is in here? P minus 1 factorial, right? P minus 1 factorial is a big number, right? Does it have an inverse modulo p? Is there a value, p minus 1, is a coprime with p or not? I don't care if it's a big value. Is p minus 1 factorial coprime with p?
Yeah.
Why?
It's always coprime with P.
Yeah, well, why?
Right?
What does it mean to be non-coprime with p?
That I can factor in.
It can, if it be non-coprime, it will have to divide by p.
Yeah.
1 times 2 times 3 all the way to p minus 1. Can that divide by p?
No,
Why not?
because they're all coprime.
Because to divide by p, you have to contain p in your factorization, right? If p is 19, the only way to get a multiple of 19 is to have 19 in your factors. But 1 times 2 times up to p minus 1, there's no p in there. P is a prime, right? P is a prime. So p minus 1 factorial has an inverse, right? Because this product, while it's a product of many numbers, p is not in the product. If p is not in the product cannot be a factor of p. And if it's not a factor of p, it has an inverse because modulo p prime, either you are a multiple of p or you have an inverse, right? So if I multiply this equation here with the inverse of, I want to get rid of this p minus 1 factorial, that's why I multiply it with inverse. What do I get? What? What do I get?
1.
I get, no, this one still stays. A at p minus 1 is there, right? If I multiply with the inverse, I get rid of this and of this. But A at p minus 1 there. I get A at p minus 1 equal 1 more p, which is the theorem. Okay? So how did I do this? I show here's two sets that are the same. Take the product of all elements here, or product of all elements here. I get this. Then I say p minus 1 factorial has an inverse because it's not a multiple of p. I multiply with the inverse to get rid of it. Because when I multiply with the inverse, this time the inverse is 1. Right? That's the same in arithmetics when you say x times z equal y times z. You say multiply with z minus 1, right? Why you to do that? To get x equal y. Every time you multiply with an inverse, you get rid of those z's, right? Same I did it here. P minus 1 factorial has an inverse, therefore this has to be equal with 1, which is the theorem. Now you could legitimately ask, how did you come up with such a thing, right? Right? Who comes up with two product sets and then say these are the same as that and then make the products of all these elements, right? That seems like crazy, right? Like, I mean, it works, right? That's a proof, it's valid, sure. But how can you come up with such an idea? How do you think people come up with this idea? Do you think the people who wrote the book, they came up with this idea? No, they read it somewhere. So who came up first with this idea? How does somebody comes up with this idea?
Someone who doesn't spend Friday evenings with friends.
Not quite. Yes, but the reason to come up with that idea is that whoever came up with this proof knew Eulers Theorem. Whoever made this proof the first time and everybody's like, nice, we can make this proof now because we got it from this guy. They knew number theory. They didn't just dream it up, okay? So in that sense, this proof is not a good mathematical education. Why? It shows the result and it's true. It hides the underlying structure, which is defined by Eulers Theorem. He did it like we did it. He construct that P of A and then to the quotients and observe that P of A times Q of A is C of N. So then he figured that out. it studied the underlying phenomena and then concluded the result based on what it observed. This is extremely hard to be based on observation. If somebody gives you the idea, you can make it, but... So we can prove Fermat's theorem this way, but for us it's not necessary because it's just a particular case of Euler. So that particular case, we have P of P here. I want to take a different case. So I'm slowly moving to module 2, which is counting and sets and counting. I want to take another n and say, okay, if n is prime, I got phi of n p minus 1. We all understand that. But what happens if n is p squared? That would be, let's take, for example, p squared. Let's take 25. That's a p squared. And who is C25? The coprimes with 25, right? What are the coprimes 25? 1 is there. 2, 3, 4. 5 is in there? No.
No.
So 6, 7, 8, 9. I'm skipping those, right? 11, 12, 13, 14, skip. 16, 17, 18, 19, skip. I'm not putting anything there. And then I get 21, 22, 23, 24, right? That is the coprime with 25? Okay, so how many things are here? Phi of 25 is the size of this set, which is 20. How did you come up with 20? You count them, right? Is there a formula, like easy to not count them? I would like to do this counting. I would like to say, okay, how do we do intelligent counts here? Of course, we can write them down and see what we get. I get that. But how do we do it fast? I would like to say, I would like to express this as a difference. Instead of counting the coprimes, which we do here, I would like to count the non-coprimes. So I'm going to write this as Z25, all the remainders, minus who? Minus those remainders that have a certain property.
Or multiple of 5.
Very good. Meaning P divides X. P is 5, right? My statement here is that to count the coprimes, it will be okay to just count the non-coprimes and subtract them from the big set, right? Does it make sense? Instead of counting the ones that have no common factors, aka they are coprimes, I'm going to count the ones that have common factors. Take them out. Well, how many things have common factors? What is this set? That's 0, of course, right? 0 is a multiple of P. What's the next one that's a multiple of P?
5.
P, right, 5. What's the next one? 2P, right? 3P, 4P, so on and so forth. Those are the multiples of P, right? The only way to get the multiples of P. The only question is, what's the last one? What's the last multiple of P that fits in here? The multiples of P are listed. That would be 10, that would be, what, 15, 20, so on and so forth, right?
P, right?
P times P is what?
The last one.
P squared. Is P squared in this set, Z25? No, Z25 goes from 0 all the way to, what's the last element in Z25?
24.
24, which is P squared minus 1, right? The last element in Z25 is N minus 1, N is P squared, so it's 24. So is P squared the last value here? No. The last value is the previous multiple of P, which is who?
P squared minus P.
P times P minus 1. There was a question? No. So how many multiples of P are here? 0, 1, 2, 3, 4, up to P minus 1. How many are there?
Yeah, P.
Let's do it as an example. Well, it's 0, 5, 10. In my example, what's the last one that's there? 4 times 5, right? So how many are there? If you count starting from 0, 1, 2, 3, up to P minus 1, how many multiples of P we have there?
Minus 1.
5 or 4?
5.
5. 0, 1, 2, 3, 4. So this set here, this set has P multiples of P. So now if I do the difference, I say, aha. Okay, so how many elements are in Z25?
25
Yeah,
minus
25.
P.
It's
Or
P squared, right?
Squared minus P.
Minus P. That is P times P minus 1, right? So now I've got the formula. Every time somebody gives me an n that's a P squared, I don't have to count the coprimes. I could just use that formula. Let's try this out. What if P is 3? P squared n will be 9, right? Who's P of 9 according to this formula? P times P minus 1, right? Which is 6. Is that true? There are 6 coprime numbers in Z9. 1, 2, 4. We got it. Right? So I can compute phi much faster, in this case, P squared. So I've got now 2 formulas. If it's a prime, it's P minus 1. If it's a prime square, is P times P minus 1. What about if it's a prime at any power? Can I repeat this reasoning here for a prime at any power? I say phi of n can be computed as the size of that, the whole remainder set, minus the size of all the remainders in there that have the property that P divides them. Is that true? The only non-coprimes are the ones that are multiple of P. Is that true? How do we get the non-coprime modulo pk? Like if P is 3, n might be 3 to the 5th. That's what? 243? Say? I say the only way to get remainders that are not coprimes with this is that they are a multiple of 3. Because the only factors in this n are 3. 3 times 3 times 3 times 3 times 3. So everybody which is not a multiple of 3 has to be a coprime. The only excluded ones are the ones who are multiples of P. Who's with me? It's the same reasoning, but instead of P squared, now I have P at some power, random power. The coprimes that I need to, the remainders that I need to exclude here are the multiples of P, just like before, because everybody else, it's a coprime. We got that? Well, let's count them again. Like here. Which ones are those? Which ones are the multiples of P? 0, of course. P, 2P, 3P, 4P. What's the last multiple of P that's still a remainder, a valid remainder? P times what? Is it P at K minus 1? P times P at K minus 1 is what?
P to the K.
Is P to the K in this set? N is P to the K. No. This set ends where? The last element, the last reminder is P to the K minus 1 down, right? It's N minus 1. So P to the K is not in there. What's the last one that's still in there? P to the K minus what? I think it's p to the k minus 1 minus 1 like that. That would be, for my example with 3, those would be 0, 3, 3 times 2, 3 times 3. The last one would be 3 times 3 at 4 minus 1, right? Because if I make 3 to the next immediate value, 3 to the 4, I get n, which is not in the set anymore. So this is the last value in there. How many people follow me? That's a little bit, it's counting. That's what we started now, part 3 of the course. It's counting. So we count. Right? Again, what are the multiples of p in Z 243? That's 3 to the 5th. 0, 3, 3, 3 times 2, 3 times 3, and on. What's the last multiple? Well, if I put here 3 to the 4th, I'm a little bit too high because 3 to the 5th is n, which is not in the set. So the immediate previous value, 3 to the 4 minus 1, is the one that I need. So how many things I count here from 0, 1, 2, 3, up to 3 to the 4 minus 1? What's the size of that? The size of this is pk. The size of that is? How many elements are in here? From 0 to orange minus 1, how many elements are there? 0, 1, 2, 3, up to the orange minus 1. Orange, which is this value, is p to the k minus 1. So this, of course, is p times p to the k minus 1 times p minus 1. So now I have a formula for phi if n is a power of a prime number, like 3 to the 5th, for example, or 5 to any power. Let's do another example here. If n is 17 to the power 20, 17 is a prime, what would be phi of n? I apply this formula, right? What do I get? 17 is a prime number, that's my p, and the power k is 20. So what do I get of phi of n if I apply this formula here? 17 at 19 times 16. Again, how did I come up with this? I took all the remainders, that's p to the k, and I took out the remainders that are multiples of p, because those are the only ones that are not coprimes. So I count them. 0, p, 2p, 3p, up to the last one that's still in the set, and I observe there's exactly p at the k minus 1 of them. So I made the difference. I take a common factor p at k minus 1, I get p minus 1. Okay, so we're making progress with this phi. We now have a bunch of phis. We have the phi for a prime number, we have a phi for a prime power, and you also got the phi from RSA, p times q, right? We also have a formula for that one. That one can be done the same. We want to take out the multiples of p and the multiples of q from the set. And we can do so. But what we want to do is a general formula for phi. Something that works for any number. So to do that, the general formula for phi, we need something that's called Chinese remainder theorem. Chinese remainder theorem. Here's what that theorem says. If I take A, B, C that are relatively prime to each other, on one hand, I consider the set of reminders modulo product let's say A is 3 times 4 times 5. They don't have to be prime numbers, but they are co-prime with each other. Like 4 and 5 are co-prime, 3 and 5 are co-prime, so on and so forth. On one set, I take ZABC, which is who? How much is A times B times C? For me,
60.
60. And on the other side, I take what's called a Cartesian product. I think you've seen it before. ZA times ZB times ZC. What are the elements of a Cartesian product? So who's, in this case for me that would be Z3 times Z4 times Z5. Who's Z3? What are the elements of Z3? 0, 1, 2, right? What's Z4? 0, 1, 2, 3. So let's write that down. This is 0, 1, 2. This is 0, 1, 2, 3, and 2 and 3, right? And who's Z5? 0, 1, 2, 3, and 4. How do you take, this is a set, the Cartesian product. How many people have seen Cartesian products? Hands up so I can see them. Okay, this is a very simple thing. How do you make, what's an element in a Cartesian product? How do you get an element here? This is a set. What's an element of it? If it's a product of 3 sets. You take one for each. The set in here is a pair. Like some reminder, say 1 with 3 and with 1 again. That's an element. Another element would be take the 0 in here, take the 2 in here, and take the 1 in here. That's another element. This is different. Remember when I said before PA times QA in that theorem before? I didn't use this sign, right? When we say PN times QA in proving Lagrange theorem, what sign did we use between PA and QA? We use this sign. This means literally make the product, right? We took a number from here with a number here, we make the product. In here, we don't make the product. In here, we just write 3 elements as a triplet. We can call this a triplet. What's another element? A 2 with a 2 and with a 0, that's another element, right? You can choose anybody from here, with anybody from here, with everybody from here. Yes?
Does that mean they're multiplied or just?
Not multiply. It's literally the element is the triplet. Before, when we do this, we had a small problem at the very end. We said, can you make a product and get the same value? That's a legitimate concern, right? Because if you do 10 times 6, that's the same as 12 times 5. The same as 15 times 4. So when we did this set, it was complicated because we had the issue, okay, when you make the products, are you going to get repeated values? In here, we don't have that problem. We don't make the product, so there's no repeated values. Every triplet is different. It's like the pants and shirts example. Every pant with every shirt gives me a different combination, right? If you don't like triplets, you can call it combinations or ways to dress up. These are the pants, shirts, and the hats. Every pant, shirt, and hat creates a unique combination.
But that's only the order matters.
For what? Order matters. This is not the same as 2, 0, 1. In a triplet, very good observations. Order matters. So this one comes from what set?
Z3.
This Z3. The 3 comes from what set? 1 comes from this set. What about the element 3, 1, 2? What about this?
Doesn't exist.
Doesn't exist. Why not?
There's no 3.
Because 3 does not exist in this set. So this is how Cartesian products work. You take an element from here, one from there, one from there. The triplet is not a set. It's an exact sequence. Okay? Now, what the Chinese reminder theorem says, that if those A, B, C, 3, 4, 5 are relatively prime, there is a function that gives you this It's called one-to-one. Anybody heard of one-to-one correspondence? What does it mean? What's a one-to-one correspondence between two things? Between the number of students in this class and the number of movies available on, I don't know, cinema. What's a one-to-one correspondence? Yes.
For every student, there's a single movie.
And backwards. For every movie, there is that corresponding student. It's one-to-one means pairing. If you don't like the word one-to-one, think about us making pairs. If I make a pairs from students to movies, every student will be paired with a movie uniquely. A movie only corresponds to a student only corresponds to a movie. Right? So you can think about between men and women, like marriage is a sort of supposedly one-to-one type of thing, right?
So weird.
Right? So every guy is going to marry a girl, and every girl is going to marry, it's a pairing, okay? You can find many examples of pairings. One-to-one means pairing. The Chinese remainder theorem says there is a pairing. So here's the pairing. The pairing is very easy. H is the one-to-one function. That is a pairing. H has to take a remainder in Z60 and pair it with what? What is an element in here? What is an element in here? A triplet. So this H, which is the Chinese remainder function, takes a guy from here with a guy from here, right? And makes the pairing. And that's one-to-one. Everybody here has a correspondence in here, and everybody here has a correspondence in here. Not two ones have the same triplet, something like that. So here's the function, it's very easy. Every time I take an X in Z ABC, that's Z60, H gives me H of X, which is a triplet. Here's the triplet. I take X mod, what is A? Mod 3, X mod 4, and X mod 5. Okay? You guys follow me? I can take any remainder. What are the reminders modulo 60? 0 to 59. I can take any such remainder and do modulo 3, modulo 4, and modulo 5, right? Well, I'm going to get a triplet. Is X modulo 3 going to be guaranteed in Z3? Yeah. X modulo 4 guarantees in Z4? X modulo 5 is guaranteed in Z5? So that's easy to see that if I do this particular operation, I get a triplet. For example, if X is 46, who is H of X? H of 46. I have to get these three reminders, right? 46 modulo 3 is 1. 45 plus 1. How about modulo 4?
Also one.
How about modulo 5? How about if I take X equal 13? How much is 13 modulo 3? Modulo 2? Modulo 4, sorry. Modulo 5?
3.
How about if I take X 17? Is what?
2.
How about 52? Modulo 3? Modulo 4? Modulo 5?
2.
We getting how this works? The tricky part is it always works the other way too. If I take those three things, any triplet, there is a unique remainder in Z60 that has this property. Yes.
It's always 3, 4, 5.
No, any ABC that are co-primes with each other. So it could be 7, 20, and 19. Every three ABC that are relatively prime. So A and B doesn't have common factors. It won't work for 9 and 6 and something because 9 and 6 are not co-prime.
But do they have to be related to
X
X?
is any value, X is anything in Z60. I pick a bunch of X's just to show the examples. How many people follow me here? How did I build this mapping? I take the reminders in Z60 and I build those three. And what you have to prove at home is that it works the other way. That if you take any three reminders, modulo 3, 4, and 5, they correspond uniquely to one reminder in Z60. There's two proofs of this in the notes. Now, one way it's easy, the other way is a little tricky, but not too hard. So, why is this important for us? That's a nice theorem, right? What this one says, not only Z60 corresponds to that, but also the coprimes corresponds to the coprime of 3 times coprimes of 4 times coprimes of 5. That's easy to see. A coprime, if X is coprime with 60, then X mod 4 is going to be coprime with 4. That's a very, very simple exercise that could have been in your homework. If you take remainder 52, it's not coprime with 60. But if you take a coprime remainder like 17, what you get are going to be coprimes with 3, 4, and 5. Because if you take somebody that has a common factor with, say, ZB, when you take this back, you're going to get something that has a factor with B, which is not a coprime with Z60. This right here allows us to factorize phi, because the size of this is phi 60. So then phi of 60 is phi of 3 times phi of 4 times phi of 5. And in the general case, if phi is some p at k times another prime, is p1 at k1 times p2 at k2 times p3 at k3. That would be phi of p1 at k1 times phi of p2 at k2 times phi of p3 at k3. So this is a general n. Any n can be factorized into primes, right? At powers. And then this theorem is telling me that if I'm to compute, for example, phi of 60, I have to factorize 60. 60 is 2 to the 2 times 3 times 5, right? Then phi of 60 is going to be phi to the 2 to the 2 times phi of 3 times phi of 5. But I already know how to compute phi of a power of a prime. Don't we have this formula here for a power of a prime? Any power of a prime, I already know how to do it. So that gives me a general formula for phi. Let's take another example. How about phi of 100? How do I factorize 100? 2 squared times 5 squared. So phi of 100 would be phi of 2 squared times phi of 5 squared. I know how to write the formula for powers of a prime. So 2 squared would be 2 at 1 times 2 minus 1. Phi squared would be 5 at 1 times 5 minus 1. So this gives me 2 times 40, 80 prime numbers with 100. 2 times 20, 40. So this theorem allows me to do this factorization, to break phi into coprimes, just like n breaks into coprimes. And then for each power of prime, each factor in n, I get a formula. That gives me the whole phi of n formula for any n. That's in your homework, this phi of n formula, okay? Are we done with the attendance sheet? Have a good weekend. You too.
Are you doing that tonight? Did you record everything?